Hi, I'm Dan Sweet with Vertical Aviation International, and welcome to our weekly or now monthly webinar series. Today's topic is artificial intelligence and security for autonomy in aerospace. This is a topic that has been getting more and more attention lately. We actually did a webinar a couple of months ago on how artificial intelligence will be able to assist pilots in the cockpit. But just like everything else nowadays, where there is a very bright and positive outlook to artificial intelligence and use of it in our industry, sometimes there can be darker sides to it. Whether it's using AI to detect security, provide security for aerospace, or the use of AI to attack aerospace, chances are somebody's going to be giving things a try. And so we thought it would be an interesting topic today to bring to your attention. So let's go ahead and get things rolling. Let's see here. There we go. Our speaker today is Dr. Kyriakos Vamvoudakis. I'm sure I just butchered that. He is an endowed professor of aerospace engineering at the Daniel Guggenheim School of Aerospace Engineering at the Georgia Institute of Technology, more commonly known as Georgia Tech. He received his bachelor's degree in electronics and computer engineering in Greece and his master's and PhD at the University of Texas in Arlington. During the period of 2012 to 2016, he was a project research scientist at the Center for Control, Dynamical Systems, and Computation at the University of California, Santa Barbara. And he was an assistant professor at the Kevin T. Crofton Department of Aerospace and Ocean Engineering at Virginia Tech in 2018, until 2018, excuse me. Vamvoudakis is a highly accomplished in robotics and artificial intelligence research. In addition to his work here at Georgia Tech, he currently serves on NASA's Secure and Safe Assured Autonomy Project team. If this is your first time joining one of our webinars, we welcome you. We're glad to also have the people who have returned to visit us with us again. We encourage interaction on these webinars. This topic, I'm sure, can be fairly technical, and so if you have a clarifying question you want to ask, please do so. Please use the question module within Zoom. The chat feature, please go ahead and use it. If you want to chat amongst yourselves, that's fine. Tell everybody where you're from, whatever you might want to do. But if you have a specific question on today's topic, please use the question module either on the bottom of your computer screen or on the side of your phone screen or wherever it might show up normally. We will do our best to get through all the questions at the end of the webinar. We'll hold those until the end and then run through those. We'll see how we get to do on time. The webinar is being recorded today. If you missed something, if you want to go back and review something, or if you want to share the video, which we strongly encourage, we know that not everybody can be online at the same time, especially midweek during the work days on the East Coast, West Coast, around the world. We'll make that link available as soon as we possibly can. And that should either be tomorrow afternoon or possibly as late as Monday, depending on how long it takes to render and other technical issues. So let's go ahead and get started. Dr. Vamvoudakis, welcome to our webinar. Thank you for taking the time out of your schedule to do this.
Thank you very much, Dan. It's a pleasure being here. Thank you for the invitation, and thank you to everybody for being here.
Well, I think most people are most familiar with artificial intelligence right now through programs like ChatGPT. And we know that it was originally designed, I believe, ChatGPT to help coders with some of their computer technology. And so there is so much work that artificial intelligence can do to benefit society. But again, there's obviously always a darker side. And it sounds like NASA and your team have been doing a lot of work to help try to make sure that things don't go the wrong way.
Exactly. Yeah. So again, AI has been very popular nowadays, especially with all the computational power we have. So AI is nothing new, though. You'll see in my presentation. So AI has been around for more than 30 years now, but it has been going up and down. But now is the time because we have all these components that we can solve very fast. So we have the computational power to do. And
that is true. My first computer, first time I ever played with a computer, we had to load the program off cassette. So I just aged myself dramatically. I'm going to go ahead and turn my screen off and let you go ahead and run through your presentation.
Sure.
I'll keep my microphone microphone on if you have any questions or anything like that.
I think you can see my screen, right?
Your screen looks good. Yes, go ahead.
Perfect, perfect. Again, so thank you very much. So I will try to be non-technical. So that's probably one of the few times I give non-technical talks, but I'll try my best. And again, I consider this as a discussion. So anytime you have something, I will be happy to answer any questions you guys have. So as Dan said, I'm a professor at the Daniel Guggenheim School of Aerospace Engineering. I've been here for 5 years, and I work on control theory, autonomy, and anything that has to do with security as well for autonomy. So So in this audience, I would like also to describe what is autonomy. Okay, so autonomy, actually it's a Greek word. So it's the capacity to make an informed and uncoerced decision. So here I found a very old figure. So where you can see that the involvement, hopefully you can see my my cursor. So the involvement from high to low, okay? So of course, when a person does very direct manual control, okay? So of course it has a high involvement. And as I go towards high automation and high involvement, then I go to autonomy, okay? So you will see more about that. So again, autonomy is anything that it is smart and doesn't involve any humans, okay? So somebody can tell me, okay, how about the Tesla? So again, that the human always has to touch the steering wheel, okay, and then it doesn't work properly in some streets. But we can talk more about that later. So as Dan said, so we are part of a very accomplished team that we work on a very big project with NASA. I think it's about $8 million. And so it is led by North Carolina Agricultural and Technical State University. Georgia is part of the consortium, so Purdue, Sky, General Atomic, Northrop Grumman, Aurora, so on and so forth. So we go from perception all the way to verification, and we want to make sure that when we deploy this urban air mobility on the skies, everything is safe and secure. Okay, so let's actually start describing more what is autonomy, or what is autonomy in an engineering lens, okay? So what we want to do is we want to make autonomous the whole ecosystem, okay? So even if we have multiple components in the system, for example, let's say we have multiple planes flying together autonomously and so on and so forth. So we want to make sure that everything talks to each other in a smart way, and based on that, they make smart decisions, okay? So again, NASA defines autonomy as the ability of a system to achieve goals while operating independently of any external control. And I mean, external control can either be a human or even a computer sending commands offline. Okay, so autonomy requires self-directedness and self-sufficiency. Okay, so what we want to do is we want to achieve goals, and we want to operate in long-term missions without intervention by the human. Okay, so I want also to differentiate what is not autonomy. Okay, so autonomy is not just AI. Okay, of course AI is a very useful component of autonomy, but it's not just AI. Okay, so there's many things that actually autonomy comes with. So several machine learning algorithms. So machine learning is actually under AI, and it can be differentiated in 3 categories. So supervised learning, unsupervised learning, and reinforcement learning. Okay, so the perception is just what I can see. Okay, how can I perceive my environment? And there's also different other things, like how, for example, let's say I drive my Tesla, and then I classify this as a stop sign, so I have to stop, and so on and so forth. So also autonomy is not automation. So the space missions, they rely on automation. So I'm sure you're familiar with Curiosity or with Ingenuity. Okay, so all these things, they rely a lot on automation. And of course, autonomy is not always and only about making systems adaptive, intelligent, smart, or unmanned. Okay, but we want to make them self-sufficient. Okay, we want to make them smart. Smart not in a way that they're just making the decision making, but also they're self-directing themselves. Okay, and of course, human is also part of the autonomy, right? So humans, they interact with autonomous systems and so on and so forth. And one actually a very simple scenario that you can think is about air traffic control, right? So humans, they can interact with decision makers that they can happen from AI to how to reroute aircraft and so on and so forth. Okay, so why we want and everything actually is going towards the direction of autonomy. Why? Because decision making can exceed communication limitations, and then we have to be smart on what to transmit and when. Okay, and also when time critical decisions must be made, we need to be very smart on what we do. Of course, when you have decisions that they're shared between multiple components, like multiple drones flying together, multiple aircraft flying together, and so on and so forth. So they have to exchange information, and then together they have to reduce the complexity and they have to improve their robustness. So of course, when we don't have centralized decision making, and we have distributed decision making, so this actually can make our system smarter and can make them reduce complications and costs of the system. Of course, when we have autonomy, so we don't require or we reduce variability in training and proficiency. Okay, so again, autonomy in airspace goes from the Earth towards Moon, Mars, and so on and so forth. Okay, so for example, Earth launch and landing systems, Earth atmospheric systems, ground systems, robotic Earth orbiting systems, human Earth orbiting systems, robotic space systems, and human space systems. All these things, they require as much autonomy as possible. Okay, so let's see how slowly we can get into what part of AI makes our system autonomous. Okay, so what we want to do is, instead of just using AI, for example, I think Dan said about ChatGPT, right? So ChatGPT is just a large language model where it is trained, and then it will give you some answers, right? So what we want to do here is we want to have, and all of them are open loop, right? So in other words, what I mean by open loop is I don't get feedback from the environment of how good I'm doing, right? So for example, I'm sure if you try ChatGPT or OpenPilot, whatever they call it from Microsoft, you will see that it will give you sometimes bad things. Bad things, very sloppy, but you can always improve them. Okay, and by asking it, okay, you need to improve it there, you need to improve it there, you need to improve it there, so on and so forth. But we want to have this improvement in a loop that doesn't require this human intervention. Okay, so there is something very popular in control theory, which is my main focus area, where it's called feedback loops. Okay, so you can think that I have an aircraft or I have a drone. Okay, so I measure things with my environment, from my sensors, and based on what measurements I get from my sensors, I can command my actuators of the system. Okay, so this is where feedback comes into the game. Okay, so what we want to do and why actually AI is very important in aerospace, and I think I don't know a single faculty in my department that doesn't work in AI for aerospace, is because they can process extremely large data sets. They can find correlations and trends that humans, they cannot find. They can actually replicate some functions without necessitating humans. They can understand data, speech, and text, and they can offer a high level of automation and consistency. Okay, so, and there's many quotes by several people from Sebregat, for example, here from John Hanlon. He said that I fully believe you can have a static set of code modeled from elements from machine learning operating an aircraft at a level of safety that meets or will likely exceed human performances in similar circumstances. Okay, so the high impact areas within AI are smart maintenance, better fuel efficiency, training, and innovative product designs. Okay, and of course, if we do innovative product designs, we can also improve our customer service. Okay, so now what you see on the left, you see two axes, right? So one axis is the AI, the other axis is the autonomy. So here on the left, you can see the manned aircrafts, while on the right, you see several unmanned aircrafts, right? So, and then here, you see two angles, right? So I try to be very vague here. So you see two angles. You see alpha and beta, okay? So I'm sure that you all can understand that from my bad figures, that A is bigger than beta because the humans, they are better at flying these aircrafts and they know what to do and what not to do, okay? So still, we have lots of work to do in the unmanned scenarios, okay? And I think in probably like 20 years, everything will happen in an unmanned way. So I don't think there will be any manned aircrafts anymore. Okay, so again, what we want to see here is, so you have a pilot, okay, let's say in this aircraft, okay? And the pilot makes the decisions, right? Instead, on the full autonomous aircrafts, so we don't have a pilot, but we have software, right? So the software, which actually has to operate like a pilot, has to make these on-aircraft decisions for flight critical times, okay? So nowadays, again, we have the pilot can make decisions in real time. Bridging this thing now between the pilot and the software is very important, okay? So again, the pilot is of course better trained, can make better decisions, okay? And while the software sometimes can make mistakes, okay? So we need a lot of improvement there. Okay, so we discussed a lot about autonomy, okay? We discussed about AI. So I think in the talk, you saw a lot also about security, okay? So why we want to be secure is, again, the smarter our systems become, the more vulnerable to adversaries are, okay? So, of course, if you make anything smart, right, everything depends on software. So this software have holes, and then people can actually access them and send different commands. So, for example, instead of bombing, I don't know, one area, bomb area B, okay? Or things like that. Okay, so so all these things are very important. So, and I actually have this this very fun script here. So that security is the North Star in enhancing autonomy. Okay, so again, FAA needs to work together with the people working AI to make better and more secure algorithms, and actually quantify what do we mean by secure. You'll see pretty soon what I mean by that. Okay, so several coverage on all these attacks that have been everywhere, right? So imagine if these things happen just to pilot aircrafts. Imagine what happens when you have just software piloted aircrafts, right? So, I mean, there is, I'm sure if you search for them, you'll find lots of news about all these things, okay? So that's very important. So there is, we have to mitigate these attacks, or even we have to make our controllers that they are part of this AI to be very robust to these attacks, okay? And again, there is, somebody can say, okay, so the attacks evolve, right? Even if you find some patches for some other attacks, the attackers can find new attacks, okay? So, because they evolve through time. So you'll see what are what we can do for those things. Okay, so some thoughts on what we can do to prevent cyber attacks, okay? So of course, train our pilots and maintenance staff, okay? Keep our software and systems fully up to date. Again, these are just suggestions for these things. Maybe there are other things. ensure endpoint protection. Okay, so any connection, for example, to fight a software system, use firewall, backup flight data, control who has access to your flight systems, and of course, provide wireless communication security. Okay, so of course, as I said, nothing is perfect, right? There might be doors for adversaries to attack and make our autonomous system, or even as you saw in the news, our fighter, our pilot aircraft systems like F-35 to be vulnerable to attacks, right? Okay, so it is twofold. Okay, so the environment in which the AI model is built and the data set used to train the AI model. Okay, so these are the sorts of safety risks. Again, so every time some adversary wants to do something, it can change the data in these two things, and then it can make our system to do whatever they want. So again, these are very important, okay? Again, we can do impacting the environment, can cause the model to be skewed from its purpose, and so on and so forth. Okay, so what we can do now, okay? So we have very unique risks that need to be considered. So several advanced frameworks must be developed to provide protection against these risks, okay? So there are two things we can do, either to train the people to work together with AI, okay? And based on that, try to see, for example, we have another project with the Department of Defense, where we want to train human analysts alongside AI to predict attacks that can happen in drones, for example, flying over Iraq, okay? So we want the analysts to be trained together with this AI to differentiate attacks, for example, from a wingcast, okay? So is it an attack or is it a wingcast? Or something happening there? Okay, so the most known AI threats are model logic threat, model bypassing, and of course, all these things, I mean, I can explain to you. For example, the model logic threat is an attack aimed at extracting the deployed models for reverse engineering to influence future training. Model bypassing is a form of attack to create conditions to evade the innovation of the model in its entirety, to alter system response, and so on and so forth. Okay, so of course, in a fighter jet cockpit, okay, so people can do spoofing, exploiting, denial of service, counterfeiting. They can change the communication systems, the navigation and flight instrument systems, the flight control systems, which is actually something that we heavily work on, the traffic and terrain safety warning systems, and so on and so forth, okay? So these are the doors for an adversary to actually change what they do during flight. Okay. So again, there's several studies on vulnerability and attacks specific to AI. Of course, they're everywhere. And if you want to have any of those, just let me know. Send an email. I will send you any of those. Okay. So what we want to do in our lab and also in the project actually that Dan said from NASA is we develop these new technologies that are, of course, they're AI-based, okay? And they're secure and they learn on the fly without any pre-training, okay? So, of course, in order for us to do that, we have to consider the limitations. What I mean by limitations? So whenever you are communicating, you have bandwidth, energy, and privacy communications, right? So the more you transmit information, the more vulnerable you are to any type of attacks, right? So the least you transfer anything, so I mean the least vulnerable you will be. Okay, so our lab works towards bringing together these three things: autonomy, security, and coherent data integration. Okay, and we have shown that to aircrafts, ground vehicles, underwater vehicles, and other structures. Okay, so all these things that you saw here, they can actually come together on something that we will call as a cyber-physical system, okay? So you can consider that an aircraft is a cyber-physical system, okay? Because it has a bunch of sensors, actuators, it has processing units, and so on and so forth. So we can call it as a cyber-physical system. Okay, so let's see what we can do now. Again, this is what I just said, okay? So a cyber-physical system is something that gets cyber parts, which, for example, you can think about any embedded computers, okay, into the physical world via sensor and actuators, okay? So again, I want you to see that everything that we will do here is because we are in safety critical applications like aircraft and so on and so forth. We have to be guaranteed to be stable, and we will use everything in a feedback loop, okay? So I'm sure you have seen the problems of robustness and stability of training with AI, because all of them, they're open loop so that they get sensing from the environment. And they work only on cases that they have been trained with. So what we do here is we don't pre-train, but it's a more of a plug and play framework that eventually make all the systems optimal, robust, and stable. Okay, so again, you can think that here is your sensing and actuators, right? So you can think that these are your perception, okay? So this is where I am, and then you communicate through a network. Okay, so again, this is just some things of what is physical space, what's cyberspace, and what is a cyber physical space. Okay, so again, don't worry too much about it. Okay, so but what I want you to pay attention is, for those of you who are familiar with embedded systems, okay, so this is just another word of talking about it, but everything is through a network. Okay. So we're right on time. Okay, so what we want to do, and then you see on the left, you see different applications, right? And you see how they evolve, okay? So you have the AI, automatization, online, offline, so on and so forth. Okay, so let's now see how all these CPS approaches, cyber-physical systems, they can be used in aerospace. Okay, so what we want to do is we're going to bridge the real world with the virtual world, okay, through the sensor network. We want to collect data, communicate between different agents. And then, for example, let's say, again, you have multiple aircrafts flying around. They have to exchange information. We have to see what information from all these things is useful and what not. And based on that, make these smart decisions. So again, what we want to do is, in order for the cyber to be bridged to the physical world, okay, we need to acquire spatial information about the physical system. Again, what I'm measuring, when I'm measuring, so velocity sensor, GPS, and so on. Okay, so there is something that we will call as a CPS hierarchy, okay? So for example, let's say you can have a very, very large, complex interconnected cyber-physical systems, which can be an electric power grid in space, a smart farm, a smart colony in the other planets, and so on and so forth. You can also have an intermediate CPS, and which, for example, a smart factory, a smart space outpost, and so on and so forth. Or you can have a small one, okay, which is, let's say, a drone or a self-driving car, okay? So all these things, they go from the small to large, as you can expect. Okay, so in order for us to test our algorithms, we're using all these things in some little baby drones, okay? So of course, I always say to my students, because this thing has very limited computational and communication capabilities, if you can make the algorithms work in these baby drones, then of course, if you make it to a bigger, that you have better and faster computers, everything will be easier, right? So everything that works in these baby drones, then it will also work in the larger one, of course. Okay, so again, you can imagine that instead of having these baby drones, you have actually, for example, large flying cars, okay, urban mobility, and they fly around buildings, okay, and they all navigate around, okay, they have humans, they have different things with them, and they want to navigate around the buildings. and they don't want to crash to each other as well. They don't want to crash to the buildings, right? So in this baby drone, the manufacturer calls it the Crazy Fly. So you see the physical parts, right? So the physical parts. And you also see the sensors where you can measure what you measure, okay? So again, the sensors are bridging the physical with the cyber part, okay? And all the flight management is happening inside this embedded computer that's inside this board here, okay? Okay, so again, remember before I said that one of the keys to having a truly fully autonomous system is vehicles talking to each other in a smart way and making smart decisions on the fly. Okay, so again, the trends for the cyber-physical systems, they go from integration with Internet of Things, right? So Internet of Things can also be integrated with urban air mobility. So aerospace will be integrated with Internet of Things, and everything will be in a 6G situation, if you can say that, okay? Again, greater use of AI and machine learning, and increased adoption of cloud-based CPS, and this actually goes back to greater focus on security and privacy. Okay, so again, the smarter the systems, the more vulnerable to attacks and the more vulnerable to expose data. So that's why we have to make sure that everything is secure, private, and safe. Okay, so now let me talk briefly about how do we test these things in a lab environment. Okay, so what you see here is you can see our indoor flight facility lab at Georgia Tech. Okay, so we have two rooms. Okay, so here around you can see we have infrared cameras. So these infrared cameras, they will measure the position of the drones. Okay, so this is the facility that we fly. Also here you can see a fan. So this fan will create some disturbances into our drones, and then we will be able to see if we're robust to such disturbances. So in a situation that this flies outside, you can think this is just a windcast that will be introduced in the stream. Okay, so again, this is just the other area. So you remember that this is and not the other room that you can fly towards the other room. And then here in the other room, we have a projector, okay, that projects on the ground. And this projector can actually do different buildings. It can do different areas. So we can actually create artificial or virtual obstacles. Okay, so one as I said, one very fast way to test our algorithms in aerospace is to use these baby drones, which, as I said, they're Crazy Flies. So here you see a setting of these Crazy Flies where you can see that we have the flow deck, we have the control board, and then here you see some little balls, okay? So these balls, they actually are markers where these cameras will make sure that they're marked and give you a positioning on the ground, okay? So again, these markers are just to be positioned by the cameras. Okay, so again, for those of you who are also interested in how this can be built, right? So we have a market deck, a flow deck, an AI deck, okay? So you can think all these things are just having sensor actuators, and then everything happens in this small board. So the AI that we test for our NASA project actually can fit in this little baby board here. Okay, so again, this is how the motion capture positioning works, okay? So you have different cameras, okay? So you remember I had these little balls here, okay? So these little balls will tell me where exactly I am on the space. Okay, so again, you can see here we have three Crazy Flies, the cameras will locate them, and then we will run the algorithms on the board, and then we will see if we're successful or not. Okay, so reinforcement learning has been an AI tool for years. So reinforcement learning, I'm sure you have all heard about Pavlov's dogs, where he was using reinforcement learning to train his dogs, right? And so this is what actually every human learns, right? You use by rewards. So let's say that if you walk around and you hit yourself in the corner of the table, then next time you will not do it again, right? So every time you're improving, and every time. Okay, so this is what we want to bring into aerospace. We want to make this cognition that it makes the system smarter and smarter. Okay, so remember that here, instead of having this system environment, we can have any system that you can think. And then for us, we can touch it with our little baby drones. So again, we want to make everything autonomous. Okay, so we don't want to have any offline computations, and we don't want to have, for example, problems with robustness and stability. So what we want to do here is we want to have the RL agent, the reinforcement learning agent, to pick an appropriate control action. Okay, so in reinforcement learning terminology, this is called an actor. Okay, I know it sounds like a movie, it's not. Okay, and then how good you're doing will be actually evaluated by something that we will call as the critic. Okay, so you can think that these two are smart structures. Okay, and they will tell you, okay, so the controller that you put into the system is not as good, so improve it. Okay, again, and this works in a reinforcement learning way. And you can see that the feedback that I talked before, right? So again, I have my sensors here, they send information back to my controller, and based on what my sensor said, I will improve my controller. Okay. Okay. So as I said, okay, again, this is a goal-directed learning. Okay, and it's actually the only, from what I can see, is the one. I believe that's the only one that can achieve full autonomy. Okay, so supervised and unsupervised learning, they require lots of pre-training, and they cannot achieve a robust and stable autonomy. Also, I'm sure you have seen the accidents with the Tesla, where I think that was like 5-6 years ago, where they crashed on a track because that was not trained properly. Okay, so again, what we want to do, we want to get the best reward, right? So what I mean by best reward is sometimes the best reward is to get the least fuel possible, right? Or go from point A to point B in the minimum time, or different things, okay? So again, what we want to do is we want to have this feedback loop, okay? This feedback loop will let us influence our actions based on what our sensors are doing. Again, by influencing actions, we mean changing the actuators. Okay, so again, we are not told what actions to take. Okay, we don't say to the controller or agent what actions to take, but it will discover which actions to take based on what we want to optimize. Okay, so again, remember that we had a reward, right? The reward, we get a response from the environment, and based on that, I make my next decision. Okay, I don't say what exactly you have to do here. I just tell you, okay, you have a reward. Okay, you pass it through something that we'll call a critic, and based on that, I change my control. Okay. Okay, and again, this is the most challenge from everything, right? So to discover by itself what is the best action to do. So let's see something that we actually did a small experiment. Hopefully you can see my screen right now with the little drone flying around.
I see your screen. I do not see anything moving around inside your screen.
Okay, okay. So let's see why. So you see a video, or you see just the PowerPoint?
I see the what looks like a silhouette of a video camera in my mind. gray
Okay.
shape against a blue field. I don't see anything inside of it.
Okay. Let's see how can I do that properly. Let me see. Now I think you can see the video, right?
Yes, now I see the video.
Perfect. Okay. So what I want you to see here is, okay, so we have this baby drone that you see it here. And here on the right, okay, so I want my drone. So you have X, Y, and Z directions, right? So the red line is the desired lines, okay? And the blue line are the lines that the learning will achieve, okay? So of course, these are noisy aircrafts, okay? So of course, nothing is ideal when you go from a simulation environment to a real hardware experiment. So that's why you see some deviations, but it's eventually learning. So let's actually run it. So here, you see it flying, and then here you see how good the tracking is, okay? So again, this is the X, this is the X direction, this is the Y direction, and this is the Z direction. Okay, so you can see that it tries to learn what I want it to learn. So again, I want the blue to be very, very close to the red line. Okay. And again, we're talking about X, Y, and Z. So, I mean, here I wanted to do just an 8 shape, so a figure 8, and eventually it will do it. Again, you see all these fluctuations because it's learning in real time. Okay, so let me do it again. So again, you see the red lines, which is the desired one. And then you see the blue lines is the one that it will do with the learning. Again, I haven't put any offline computations. Everything happens in real time. So the drone learns in real time how to perform a safe 8 figure. Again, it tracks the X direction, it tracks the Y direction, it tracks the Z direction. So let me go back to my presentation. I think now you can see my presentation back, right?
That's correct, yes.
Perfect. Okay, so again, what I want you to show is I want to give you a background of what's autonomy in aerospace, what we consider autonomy in aerospace, because different people consider it different. Okay, so I wanted to emphasize how important security is in aerospace, and I want to show you also how we can manipulate even these little small drones to do what we want with reinforcement learning. Okay, so again, to conclude, so I want to emphasize that UAVs can potentially completely replace existing remote sensing systems. Okay, and this AI hype will actually change how we do things. Okay, so imagine if I can do all these things with the little small drone. Imagine if I had, for example, an NVIDIA card on a big drone, on a bigger drone, what I could do. Okay, and of course we will resolve lots of things that right now they're not solved during autonomous flights. For example, obstacle avoidance, okay, how to do long-term missions, and how to make smart decisions in a formation, and so on and so forth. So what I think also is that if we consider the interaction of the physical and cyber parts in a different way, then we can potentially change these UAVs, the swarm of UAVs, and in general aerospace. Okay, so of course, every time in an urban air mobility scenario, you have all these obstacles, these buildings, and so on and so forth. Every time you go around all these buildings, you can exactly ultimately lead to the practicality of the big data. Okay, so all these things, they will give you lots of information of how what happens in situations where you have a conflict, obstacles, and so on and so forth. Okay, so again, every day there are more things coming up in the UAV scenarios in airspace. So as we get more intuition and insight of what is happening, I think there will be a huge breakthroughs in airspace, and I'm sure you have seen lots of them. And yeah, and then we have lots of things that we're planning to work on in airspace. So of course, we want to enhance autonomy and how AI is integrated with autonomy. We also want to work on UAV delivery services and how to make it more reliable. I'm sure that you have seen lots of hype about that as well. We want also to be very efficient when we do these UAV operations. And if they're battery operated, I want also to make sure that we have fast charging capabilities, okay? So one other project that we actually we had was on securing fast charging stations from attacks that can happen either or for cars, fast charging stations for cars or for drones. And of course, we want to have advanced maintenance and repair operations and general UAV solutions. And then I think I planned for a 45-minute talk, and I guess I was 50 minutes, but I will be happy to answer any questions.
Oh, that was fantastic. Thank you, Kyriakos. We did get several questions in, so I'm going to take them in the order that they came in. Do the risks of vehicle-to-vehicle communications as a new threat vector outweigh the benefits providing situational awareness? And what do S2A2 studies and SIMS say about this question?
Okay, so to understand the question, so every drone or every UAV, it has different communication capabilities, and how this can affect security of the whole team. Was it a question?
The question again was, do the risks of vehicle-to-vehicle communications as a new threat vector outweigh the benefits providing situational awareness?
Okay. Again, the S2A2 project is about doing these flying cars. So maybe they can actually explain the questions more. I don't know what exactly.
Okay, the person who asked that question, if he doesn't mind providing a little bit more information in the chat, we will we'll go on to the next one.
Sure.
Do you see the use of emerging open ATM standards such as ICAO's SWIM as increasing cyber risk in our airspace or reducing it, and why?
Oh, I mean, I think it will increase. Every time we have something like that, it will always get attackers smarter, and they will always get find ways to get in. So I think this will potentially get more doors for threats.
Okay. The person did respond back on question one, and basically he's saying, have the risks of vehicle-to-vehicle communications been examined?
Yes. Oh, okay. I understand. Yes. Actually, the time that you exchange information between different vehicles, you're also vulnerable to several, for example, denial of service attacks and so on and so forth. Because if I want to send information of position and velocity from one drone to another drone, or from one flying car to another flying car, okay? So this can also be jammed by adversaries. So yes, we consider also communication attacks.
This is a question of mine. It seems like right now there's, particularly in the Middle East and Europe, there's a great deal of GPS spoofing going on. Is that, how did I phrase it? Is that an example of a threat to a cyber physical system? Is it a product of AI programming, or do we know how that's being accomplished right now?
Okay, so that's a very good question. So we have lots of work on GPS spoofing. Actually, before I was at Virginia Tech, And we examined how you can spoof underwater vehicles as well as drones. And spoofing can be actually mitigated if you have multiple GPS receivers on board, okay? And then what you do is you put them on different locations, and then based on that, you take a visiting agreement between all those. So because the attacker has to actually either spoof all of them together, but he mostly doesn't have the capability and the bandwidth to spoof all of them, okay? So all of the attackers, they have limited bandwidth, okay? So because they don't want to be exposed. So the time that he or she spoofs the GPS, then you will be able to see by visiting agreement, you will be able to see from the other GPS that something wrong is happening. Okay. So actually the aircrafts, they actually use multiple components right now to get a visiting agreement between all these things in case something goes bad. But I remember at Virginia Tech, I had a colleague who actually spoofed a very large super yacht. So what they did is they have been working on GPS spoofing for a long time, and then they found a very rich person, and then he was like, if you can actually spoof my super yacht, I will let you have 2 weeks free vacations. So, and then they were cruising in the Mediterranean, and then there were news all over that. So if you Google super yacht spoofing, you will find it. So what happened was that they were able to spoof it, and the captain thought he was somewhere else, but they were actually deviating from this area. And so yeah, and it was all over the news. So if you're interested in this one, that will be fun to watch.
I might have to take a look at that.
Yeah.
We have another question. For real-time airspace networks, do SIMs tell us resilience to weather events is better handled by centralized ground AI control or by decentralized distributed vehicle AI control?
Okay, yeah, that's a very good question as well. So again, the more decentralized and distributed you are, the best for you, because the attacker or whatever adversary you will have to change all these things, okay? If you have only one computer, a centralized information, the time that the attacker spoofs, changes, or does something in centralized information, then your whole mission will probably be in jeopardy. So having more distributed information and having visiting agreements between all these things is one key to mitigation of these attacks.
We also had a person ask a clarifying question. Can you explain the difference between automation and AI again, please?
Yes. So automation, you can think that when you are at your place and you actually change your temperature to let's say your AC to 69 or 70 degrees, right? So you will eventually reach this temperature, right? So this is somehow like a small automation, okay? But there is nothing smart in this one. So the time that you put something smart into automation, like for example, I'm improving over time, okay? So I'm learning over time. I'm getting better over time, so I will not do this mistake again. So then, and only then, you have a complete autonomous. So I will say that the time that you incorporate cognition in all these things, it's the answer to autonomous systems.
Okay, let's we'll start wrapping up. I got one more quick question just of my own. And maybe this is maybe something for either a personal response or something on behalf of NASA. Where do you think the majority of threats to aerospace are going to come from? Is it going to be a corporate espionage issue, a government issue, or is it going to be the random individuals or groups with an agenda that will pose the biggest threat to aerospace?
I will say all of the above. I mean, and the biggest threat will be probably some teams with an agenda. So again, the most attacks that I have seen in several drones and so on and so forth, again, they have been from China and Russia, but I don't know if it was the government or just some people. They're just some teams. They're trying to get information about things. So, but yeah, so it will get worse. So, but yeah, I mean, China and Russia, they're the responsible ones. But again, we cannot link it back to the governments, but we can link it back to different groups that they try to get information of several things.
Okay, well, I can't tell you how much I appreciated this today, Dr. Van Voudakis. This has been a really interesting topic. A lot of it went past me, I will freely admit, but no, I really enjoyed hearing it on the topic. Knowing where our aerospace industry is headed now. Obviously, things have changed significantly in aerospace over the years, and it's going to continue to change, and we have to adapt and overcome to keep flying. So appreciate your time today. Appreciate the work that you and your team are doing, and the work that your students are doing to help for the future as well.
Thank you very much, Dan. Thank you, everybody, for being here. Again, I'm always available. If you guys have any questions about anything, I think you can find my email or my information online, and then you can send me an email, and I will be happy to talk with you or answer any questions that you might have.
Got one real late question came
Sure,
in
sure.
on charging security. Have you examined the 2022 Sandia report on CCS? And do you believe ISO 15118-2 would fix it?
To be honest, I'm not familiar with that, but I can check. And
Okay. I might get that person's email address to you.
Sure, yeah. I mean, we can,
responded.
yeah.
It sounds like you provided information on how they can contact you.
Yeah.
Okay, well, again, thank you for your time. If you want to
Thank
stop
you very
sharing,
much.
then I will go ahead and
Sure.
start sharing my screen to wrap things up. And
Thank you
again,
very
please
much,
enjoy
Dan.
your
Thank you.
evening. Thank you for your
Thank you.
time.
Thank you.
Okay, well, hey, coming up next, that number one, that was fascinating. Number two, we're going to stay on a technological theme with our next webinar. Our webinars are held the second Thursday of every month at 4 p.m. Here we are today. The next webinar is going to be on the Piasecki hydrogen-powered aircraft. Right now, it's under development, the PA-890. We will have John Piasecki from the company joining us to talk about that development and in the future of hydrogen powered aircraft in general. I know that he's working with ZeroAvia on their hydrogen fuel cells. And so there's the potential for a great deal. To me, hydrogen powered aircraft are going to be coming in faster in some cases than maybe battery powered. But I believe they'll also have different applications. And so getting to learn a little bit more about the hydrogen-powered aircraft should give us an insight on where the industry is headed. Look forward to that one as well. And we're looking at topics such as employee retention and engagement for future ones. That would be something managers and workforce development people might be interested in hearing about. And we're also looking at a webinar coming up on for new pilots. Hey, you guys have just gotten your pilot certificate. You've got maybe 100, 200 hours. What's next? How soon before you can launch yourself into some of the bigger aircraft or more specific missions that you're interested in? So those are topics we're looking at. Hit the button here. VAI, we like to share information. We have a couple of publications right now. One is print, Rotor Magazine. We're going to be changing the name of it fairly soon once we come up with the right one. It's a quarterly publication, an award-winning publication, a lot of in-depth information. We encourage everybody to subscribe to that. It's free unless you live outside the United States, and then there is a small stipend included for shipping, international shipping. Rotor Daily. It's something we send out every business day. We comb through the internet to find stories that are relevant to our industry and share those with you so you don't have to do the searching. We provide sources, Google's obviously one of them. AI will probably be used more and more as well. We also reach out to the manufacturers. Our VAI members also send us information. All that comes in through Rotor Daily. Easiest way to subscribe to both is to go to rotorua.org/subscribe. We will be getting a new website later this summer, and so we'll be changing URLs to match up with our new industry name. But until then, please use rotor.org/subscribe. We'd like to know more about what you want. Please send our president, James Viola, an email letting know what VAI can do, what we're not doing right, what we're doing wrong, what we're doing well. You know, if there's something that you think that VAI is really doing, you know, maybe on advocacy or safety, we love to get positive feedback as well as the critical feedback. So please let us know. Easiest way to do that is to send a message to Jim Viola at president@rotor.org with your challenges. That does conclude our webinar for today. We are grateful that you took time out of your busy schedule to join us. Until next month, we ask that you fly safe and you be safe, and we will see you again very, very soon.